Welcome again to my study. Today we're going to talk about probability theory. In order to understand statistical studies and the way in which they function when we get to causal studies, we need to make sure that we're all on the same page about probability theory. In fact, there's probably no more useful information that you can get from a mathematical perspective for ordinary life than mastering probability theory and seeing how it plays a role in confirmation theory. So we're going to go through two sets of notes about this. The first are notes on probability theory, and then we'll do some slides on it. So one of the things I want to emphasize is how weird probabilities can be. As I understand the nature of philosophy and the problems that it generates and addresses, philosophy lives at the edge of paradox. And there's nothing more surprising or paradoxical in the mathematical domain, as far as I know, than probability theory. We think we understand probabilities at a fairly generic level, but probability mistakes are very, very common. We make them quite regularly all the time, and what to make of the degree to which we're subject to probability mistakes is controversial. What you're supposed to do about such mistakes is controversial. But I first want to introduce you to the weirdness of probabilities, and then we'll talk more specifically about the mathematical structure of probability spaces themselves. So first, some notes on probability theory. Here's some basic stuff. We're going to go over this later on, but it might be helpful just to see it in its skeletal formulation. So probability theory, there are different ways to axiomatize it. And this is one way to do it. So the axioms on this axiomatization are that probabilities are numbers between 0 and 1 inclusive, that where you have disjunctions, we're going to come back to these symbols later on. This is our symbol for or. In certain cases, when you're trying to calculate the probability of a disjunction, you can just add. Not always. You can add when the events in question or the claims in question are incompatible. The next one is sometimes it's often put in different language. Sometimes it's said where A is a tautology, its probability is 1. I'm writing where A is necessary, its probability is 1. Other presentations say where A is certain, its probability is 1. In any case, we need an upper limit that's defined in terms of what's necessary or tautological. The third thing, it's the fourth thing that we need, is some understanding of this slash. We read this in English as the probability of A given B. So there's some sort of conditionality going on, and our ratio formula, that's what this line is. The ratio formula tells us how to interpret this mathematically. We interpret it as division. So the probability of A given B has the same value as the probability of A and B divided by the probability of B. That's called the ratio formula. Finally, though we really don't need to do this, we don't need a separate clause for conjunctions. Our ampersand is our symbol for and. The probability of A and B is the probability of A times the probability of B given A. That will generate a complete mathematical theory of probability. There are other ways, even simpler ways of presenting the axioms, but this presentation is adequate. Then we start deriving theorems, and some of the most important ones are the logical equivalence theorem. If A and B are logically equivalent, they have the same probability. This is part of a general truth about probability theory. Probability theory respects logic. And this is one of the bugaboos regarding probability theory, because if you miss a logical connection, you'll get the probabilities wrong. We'll talk about that later when we come to the famous Monty Hall problem. The second thing is the total probability theory. The total probability theorem tells us that if you have a set of events that are mutually exclusive and which sum to 1, call this a partition. So here's the idea. Think of a probability space, the totality of what's possible from a probability point of view. This is our space. It's a big block of cheese. You can cut the block of cheese into however many parts you want. Just take your knife and start cutting them. Every particular way of carving up the block of cheese generates a partition. So you might have done this just cutting the block of cheese in half. In fact, if you do this and just cut it in half or cut it into 2 parts, it doesn't have to be exactly in half, that's a 2-compartment partition. But it can have as many compartments as you care to create in your block of cheese. In any case, suppose you've got a set of events that forms a partition. Then you can calculate the probability of anything on that partition as follows. You just generate a sum of the conditional probability of B on all of the partitions times how big that partition is. So go back to the simple 2-compartment partition. You want to know what the probability of B is. Well, figure out how much of the first compartment is B and how much of the second is B. That will give you the probability, let this partition be A1 and this one be A2. How much of A1 is B? That's just the probability of B given A1. And how much of A2 is B? That's just the probability of B given A2. The other factor that you have to take into account is how much of the total space does A1 occupy? Well, that's the probability of A1. And how much of the total block of cheese does A2 occupy? That's the probability of A2. So you take this number times that number plus this number times that number. Notice that's just what this says. If n is 2, then you're just going to sum the conditional probability for each compartment times the size of that compartment. The total probability theorem tells you you can do that no matter what logical space, no matter how you partition the logical space in question. Finally, there's Bayes' theorem, which turns out to be immensely important when it comes to confirmation theory. The simplest form of it tells you if you want to know how much or to what degree E is evidence for H, you're going to want to know something about the probability of H given E. And the answer to that is, first, a matter of the degree to which the hypothesis predicts the evidence. So how probable is the evidence given the hypothesis? And then there's this other thing called the Bayes factor. The Bayes factor tells you something about how surprising the data is. So what we're going to look for when we do confirmation theory is we're going to try to generate an answer to the probability of H given E by looking at the inverse probability and this division problem about the unconditional probabilities of H and E. We'll go through that with examples to see exactly how it works, but these three theorems are enormously important ones for understanding probability theory. That's some quick background that we'll come back to, but let's look at some examples. I'm going to not talk about these because some of them I'm going to talk about later on in the next set of slides. So the Chevalier de Mere gambling house case we'll talk about when we get there. Let's talk, though, about some fallacies. First, the conjunction fallacy. Linda is 31 years old, single, outspoken, and very bright. She majored in philosophy. As a student, she was deeply concerned with issues of discrimination and social justice, and also participated in anti-nuclear demonstrations. Is it more likely that Linda is a bank teller or a bank teller and a feminist? Now, it turns out if you do this and give surveys, people pick the second option. But this is one of those cases where, since probability obeys logic, probability respects logic, this probability can't be higher than this probability. So that raises the question of why psychologically people prefer the second answer to the first, and what that might show about the relevance of probability to ordinary life. Here's another case. We're going to talk about this when we get to the chocolate studies case and the issue of p-hacking, but think about the multiple comparisons fallacy. Here's how it went. In 1992, a landmark study appeared in Sweden, a huge investigation. It enrolled everyone living within 300 meters of Sweden's high-voltage transmission line system over a 25-year period. They went far beyond all previous studies in their efforts to measure magnetic fields, calculating the fields that the children were exposed to at the time of their cancer diagnosis and before. This study reported an apparently clear association between magnetic field exposure and childhood leukemia, with the risk ratio for the most highly exposed of nearly 4. Now, this is a common kind of thing reported in the news. And this multiple comparisons fallacy is something you need to always keep in the back of your mind when you see reported associations in the news. Now, what you might say about this is the following. Surely, here was the proof that power lines were dangerous, the proof that even the physicists and biological naysayers would have to accept. So scientists were in general skeptical about the idea that transmission lines cause cancer, but lots of old wives' tales, anecdotal information said, I had a friend, they lived next to it, they got leukemia. I think it's dangerous. Some of us are married to people like that. In any case, this looked like, finally, somebody produced some real evidence. It's a landmark study from '92. But 3 years after the study was published, the Swedish research no longer looks so unassailable. Why not? The original contractor's report reveals the thoroughness of the Swedish team. This is crucial. Unlike the published article, which just summarizes part of the data, the report shows everything they did in great detail, all of the things they measured and all the comparisons they made. Here's the crucial piece of information. Nearly 800 risk ratios are in the report. Okay, so you were looking for risk ratios, and your study investigated 800 of them. Now think about our margin of error estimates. Suppose you're willing to accept the significance of a study when it only involves a 5% margin of error. So you've adopted the 2 standard deviations threshold for statistical significance. Let's suppose you've done that. What's 5% of 800? 40. So if you measure 800 risk ratios, you should expect 40 outlier events, 40 outlier results, where It looked like there was an association when there really wasn't. That's what goes wrong with not the study itself, but the use of the study in the media. The study was really big, and what got reported was one part of the study. That's the multiple comparisons fallacy. We will learn more about exactly why that's a fallacy, what goes wrong with it, when we get to the topic of p-hacking a little bit later on. Here's another one, the base rate fallacy. I'm going to give a particular medical test example of this in the next set of slides, so let's go ahead and skip that one. Here's a really fun one. I'm sure all of you already know about this, the gambler's fallacy. But here's a particular incident of it, and ask yourself, what would you be doing? First, you have to be a person who lived in 1913. Second, you have to be a person inclined to an interest in gambling houses. So you're going to a casino. But here's what happened. On August 18th, 1913, at the casino in Monte Carlo, black came up a record 26 times in succession on a roulette wheel. There was a near panicky rush to bet on red, beginning about the time black had come up a phenomenal 15 times. In application of the maturity of chances doctrine, the gambler's fallacy, players doubled and tripled their stakes, this doctrine leading them to believe that after black came up the 20th time, there was not a chance in a million of another repeat. In the end, the unusual run enriched the casino by some millions of francs. Ask yourself, what would you be inclined to do? I'd be very tempted to bet on red. I'd be watching the history and saying, man, black can't go on forever, which is true. Well, actually, it can go on forever. The likelihood is infinitesimally small, though. That's a controversial remark, let me point out. Maybe there can't be infinitesimally small chances. And if you're talking about infinite spaces, it turns out the probabilities might have to be counted as zero. But in any case, we'll talk about that later as well. But ask yourself, what would you be inclined to do here? The natural human tendency is, I'm going to start betting on red. Now, what's the mistake here? Well, here's a joke. We'll talk about it later, but here's a joke. Suppose we have other worries at this point in history, but there was a time at which hijackings of airplanes was much higher on the radar screen in terms of what you risk when you go about your ordinary life. So suppose you're worried about somebody bringing a gun on a plane, sneaking a gun through TSA, getting it on the plane. You don't want to be on a plane where somebody manages to get a gun on the plane. So here's a strategy. This is the joke. Bring your own gun on the plane, because the chances of there being two guns on a plane is way lower than the chances of there being one gun on the plane. Now, you recognize how stupid that reasoning is, but it's very seductive. There's many ways in which the same kind of issue that underlies the gambler's fallacy is at work in the plane hijacking joke. It also showed up in the World War I Army Manual. In the World War I Army Manual, advice was given on what to do when you're under shell attack, and the advice was jump into a fresh shell hole, because the chances of the shelling landing in the same spot twice is much lower than the probability of it landing there once. That's a really weird thing. Okay, let's move on. The hot hand fallacy is another fallacy. This is related to the gambler's fallacy, as you can see. Gamblers who are on a winning streak start betting more. Gamblers who are on a losing streak start betting less. That's the hot hand fallacy. It's an interesting question, and partially an empirical one, how this connects up with hot hand reasoning in, say, basketball games. You will hear announcers do this, and we actually, if you ever played basketball, this is what you do. One of your players has just made 4 shots in a row. you're coming down the court. You can pass either to the guy who made 4 in a row or to the guy who doesn't seem to be on any streak. Who do you pass to? They both have equally good shots. People tend to feed the ball to the guy who's making the baskets in belief that they're on a hot streak. That looks like exactly the same fallacy, though there's some empirical work on this that would be relevant to telling whether or not it's a fallacy. Maybe there's something at work in these cases so that it's not a fallacy, but on the face of it, it looks like a mistake. The most interesting problem for the slogan that probability respects logic is the Monty Hall problem. So here's how the problem arises. Monty Hall, by the way, was the MC of the show Let's Make a Deal. There's a new version of it that has somebody else because Monty Hall is long dead. But in the original Let's Make a Deal thing, one player was selected for the last grand prize game. And the way that prize worked is you're faced with 3 closed doors, and then you're told that there's a valuable prize behind one and nothing very interesting behind the others. So suppose there's a Lamborghini behind one of the doors and goats behind 2 of the doors. 2 goats, 1 Lamborghini. This is a mean and nasty Aggie joke to come. So if you don't like Aggie jokes, when I taught at Texas A&M, everybody loved to do Aggie jokes. So here's a particular kind of Aggie joke. When I taught this problem there, I could say, if you're an Aggie, adjust your preferences so that you actually prefer the Lamborghini to the goat. Somehow they didn't think it was that funny, but I did. In any case, assume you prefer a Lamborghini. All right, so you now know the setup of the game, and then Monty says to you, what door do you want? So it doesn't matter what door you pick. I don't care. Let's just make one up. Suppose you picked door number 3. Door number 3. Now here's the way the game goes. Monty opens a door that's got a goat behind it. Once he opens the door with the goat behind it, there's your door choice and one other door choice, and then he offers you the options of sticking or switching. So he's going to open a goat door. He opens a goat door. Now there's 2 doors. You've already picked door number 3. Do you want to stick or switch? Most people on first seeing and hearing this problem just assumed it's like flipping a coin. You got 2 doors, and you got a 50-50 chance left of the Lamborghini being behind one of the 2 doors, because what you know is there's a goat behind one of the doors and there's a Lamborghini behind the other door. So do you want to stick or switch? Most people say, yeah, it doesn't matter. The probabilities are equal. Stick or switch makes no difference. Turns out it does make a difference. Your chances of winning are 2/3 if you switch. So if you stick, your chance of winning is only 1/3. Why is that so? Well, here's the simplest explanation I know of for the fallacy involved in the Monty Hall problem. There's a little piece of information that I gave you that has a logical implication that often goes unnoticed. The piece of information is that Monty opens a goat door. After you select a door, Monty has to open a goat door. He cannot open a Lamborghini door. So he has to open a goat door. So now ask yourself this. You made your initial selection, and then Monty has to open a goat door. Now, Monty knows where the Lamborghini is, and he can't open that door. So you make a choice, and there are 3 possible combinations here, depending on if you choose door 3, 2, or 1. But just stick with 3, and then we can note the symmetry between how the game plays out had you picked one of the other ones. All right, now you pick door 3, so he can't open door 3, right? So now he can open door 1 or 2 and ask yourself this. You know that if you picked the Lamborghini door, Monty has a choice about which door to open. But if you picked a goat door, Monty's choice is forced as to which door to open. So there are 3 possible things about what's behind door number 3. It's either goat 1 or goat 2 or Lamborghini 1. Depending on what's back there, Monty's choice might be forced or might not be forced. Ask yourself this question. Out of the 3 possible cases, how many cases are ones where Monty's choice is forced? And the answer to that is 2. There's only one case where Monty has a choice about which door to open, and that's when you pick the Lamborghini door. If you switch from the door you picked, you switch in a way that tracks when Monty's choice is forced. That means 2/3 of the time you will win. So there's a little noticed fact of logic in the description of the game that often gets ignored or not noticed, and it implies directly that you win 2/3 of the time when you switch. Anyway, that's the Monty Hall problem. There's a vast literature on this problem generated from the early 1990s because Marilyn Vos Savant, that's a stage name I don't actually know what her real name is, but she holds the Guinness Book of World Records for the highest tested IQ in human history. And she writes, or at least was writing a column then. Maybe it was in the New Yorker magazine, I'm not sure where it was. But anyway, this problem was presented to her and she gave an explanation of why you should switch, but I read it when it first came out and I could not make sense of it. It wasn't pellucid, let's put it that way. Well, it turns out my best friend at Texas A&M was a probability theorist in the statistics department, and we would go to lunch once or twice a week. We did that for 20 years. Really good friend, and so I presented him with a problem. I told him what Vos Savant had to say about it, and he scribbled on a napkin for about 3 or 4 minutes and said, yep, she's right. I still have the notes that he scribbled, but he solved the problem in the way a statistical probability theorist would, and the notes are beautiful. I don't actually know what the notes stand for, but it's really fun to have the napkin. In any case, she was right, but this was the same time when a book called Mathematical Illiteracy or something along those lines was published in America saying we have a problem with the national debt and other sorts of things, and it's because Americans are mathematically illiterate. They can't actually understand the difference between a billion and a trillion. They might be able to tell you what they're talking about, but they don't understand it. So it's just a bunch of zeros after the number 1. And how many there are, I mean, it's a difference between, 9 and 12 or something like that. But it doesn't register. Well, mathematicians across the country were livid and wrote in and said Marilyn Vos Savant was contributing to mathematical illiteracy because it's obvious that it makes no difference whether you stick or switch. The problem was her explanation of why you should switch wasn't clear enough for them to see that she was right. In any case, this correspondence ended up being published as a book, and it's a neat book to read. It's a fun problem, and it's very interesting to see how things played out. But apparently you can be a math professor at a major university, even a major research university in America, and not be very good at probability theory. Here's a further one. I told you about the shell holes, jump into a fresh shell hole advice in the World War I Army manual. Here's a similar problem from the 1950s that is structurally identical to the Army manual advice as well as to the take a gun on an airplane case joke. In any case, in the 1950s, people were worried about the Cold War. They were worried about Russian bombers being able to get through our levels of defense and dropping a nuclear warhead on some major city or some target in the US. So the New York Times, in good investigative journalism fashion, decided to try to figure out what the chances are of a bomber getting through our defense system. And here's what they found out. They found out that each level of defense had a 0.15 probability of shooting down an incoming plane, and that's very disconcerting during the Cold War. That's not very good at all. But they also found out there are 5 levels of defense, each having the same probability of shooting down the incoming plane. So they looked at this and they said, look, what we're really interested in is what's the probability that an incoming plane gets shot down before it can deliver a warhead? And they said that number is 0.75. How did they get that? Well, 0.15 added together 5 times is the same thing as 5 times 0.15, and that's 0.75. Now, that's a fallacy, but it's a very common fallacy, a very easy fallacy to commit. What goes wrong with it? We'll talk about this when we get to actual problems in probability theory, but let me just convince you that it is a mistake. So remember, the first thing they found out was the intrinsic probability of any level shooting down an incoming plane. It's 0.15. And then the second thing they did was we got to figure out how to enhance that number, and the way we do it is by creating extra layers of defense. Well, apparently the Pentagon thought 5 layers of defense was sufficient. Or at least maybe that's all they had money for. But what if they had done 10 layers of defense instead of 5? What would the New York Times have reported? Well, if they followed their formula, they would have multiplied 10 times 0.15 and gotten a probability of 1.5. And then even a reporter knows, this is a joke, y'all, even a reporter knows something went wrong if you end up with a 1.5 probability. Okay, we'll look at how to actually calculate that probability later on. I think the Allais paradox is the last piece of information. It's quite extensive, but it's an interesting problem. I'm not going to spend a lot of time on it right now. It's more a decision theory problem, but that's where we're headed in chapters 9 and 10. So let's look at it, the Allais paradox. You have 2 options. Choose between them. Option 1, get 24,000 with certainty. Option 2, have a 33 over 34 chance of winning 27,000 and a 1 over 34 chance of getting nothing. Which seems more appealing? Which would you choose in real life? Now, I don't care what your answer is. I would predict most of you would choose A, but I don't know. In any case, which would you choose in real life? Probably it depends on the amount of money. If you make it 2.4 million versus 2.7 million, I'd say I'll take the sure thing of getting 2.4 million, because getting 2.7 million rather than 2.4 million isn't really that big a deal. If it's $2.40 versus $2.70, maybe I'll be more adventurous and I'll take the chance of getting the 30 cents more, because it's really not gonna, if I lose out completely on $2.40, that's not that big a loss. Who knows what we'd say in real life. But here's a second case. Second case, you have a 34% chance of winning 24,000 and a 66% chance of winning nothing. Choose between that and a 33% chance of winning 27,000 and a 67% chance of winning nothing. Now, the paradox arises because of intuitive conflicts between the answers that people give in these cases. It's not really a paradox, it's just a weird thing that happens in human reasoning and its relation to formal decision theory. It was presented in 1953. I've modified it a bit for ease of the math, but the essential probability is the same. Given the first one, most people prefer A to B, and most people prefer 2B to 2A. Indeed, in within subject comparisons, a majority express both preferences simultaneously. Now, this is a problem because the 2's are equal to a 1/3 chance of playing the 1's. That is, 2A is equivalent to playing gamble 1A with a 34% probability, and 2B is equivalent to playing 1B with a 34% probability. Among the axioms used to prove that consistent decision makers can be viewed as maximizing expected utility is the axiom of independence. If X is strictly preferred to Y, then a probability P of X and 1 minus P of Z should be strictly preferred to P chance of Y and 1 minus P chance of Z. All the axioms are consequences as well as antecedents of a consistent utility function. So it must be possible to prove that the experimental subjects can't have a consistent utility function over outcomes. And indeed, that's the case. So I'm going to stop there because this is like the feminist bank teller case in one respect. People engaged in ordinary human reasoning have responses that conflict with a certain formal theory. Now, if you're certain that the formal theory is accurate, then humans are irrational. And some people like to call this a paradoxical situation. It's not actually a paradox. It's just, are human beings really consistently irrational enough as this sort of paradox, as this sort of story says? So here's the payoff to it. This is what Allais was remarking. Let's say you prefer 1A over 1B and 2B over 2A, and you would pay a single penny to indulge each preference. The switch starts in state A. Before 12 p.m., you pay me a penny to throw the switch to B. The die comes up 12. After 12 p.m. and before 12:05, you pay me a penny to throw the switch to A. You keep doing this, flipping back and forth. I have taken your 2 cents on the subject. If you indulge your intuitions and dismiss mere elegance as a pointless obsession with neatness, then don't be surprised when your pennies get taken from you. So this is something that will recur when we get to decision theory. When you violate the probability calculus in your preferences and then you're willing to act on them, Dutch books can be created against you. A Dutch book is a series of bets that no matter what happens, you are guaranteed to lose money. So let's focus on the mathematical theory itself and just see where that will take us. So first, some brief remarks about logic, because one of the fundamental facts about probability theory is that it respects logic. So we need to know what the underlying logic that needs to be respected looks like. First, here's some terminology that we will consistently employ in talking about logic. Logic concerns propositions and arguments. Sometimes people say sentences and arguments, but in any case, an argument is a set of sentences, one of which is the conclusion and the remainder of which are the premises of the argument. Arguments can be evaluated according to deductive standards, but also according to non-deductive standards. If you evaluate an argument on deductive standards, you're testing to see whether the truth of the conclusion is guaranteed by the truth of the premises. If you're evaluating non-deductively, you're looking to see whether there's positive confirmation generated for the conclusion by the premises. Now, since probability respects logic, if an argument is deductively valid, it will constrain the probabilities of the relationship between the probabilities of the premises and the conclusions in important ways. But probability theory turns out to be most applicable when we're talking about non-deductive evaluation of arguments. So for deductive assessment, we see if the pattern of reasoning is truth-preserving. For non-deductive, we want to see whether the argument makes the conclusion probable. Here are the connectives and the symbols that we use. Some of these are different in different systems. So for example, in some systems, that symbol is used for not, or is almost always the wedge. Ampersand, I like this one because it's intuitive. Some people use the caret as the symbol for and. I don't do that because it's very easy to look at those two symbols and misread the one as the other. But I've never had a case where I read the ampersand as a wedge or vice versa. But these are just structurally so much alike that I don't like using them that way. Other people use a dot, like a multiplication symbol, as the symbol for and, but we'll use ampersand. Implies is a single arrow. Sometimes people use a sideways horseshoe for it. If and only if is a double arrow. In some systems, a triple bar is the symbol being used for that. In any case, those are the connectives. So that's the underlying very simple stuff about logic and the terminology. The deductive standards, if we're evaluating an argument according to these standards, when an argument has a form that's truth-preserving, we say it's valid. An argument can be valid even though it has false premises. So we want to know, what do we call an argument when it has true premises, as well as being valid, and there we say the argument is sound. So here's an example of a valid argument that's not sound. All whales are fish. Shamu is a whale, so Shamu is a fish. That's an argument that has validity in that the conclusion follows of necessity from the premises, but it's not a sound argument because whales aren't fish. When it comes to non-deductive arguments, the relevant formal property that we're looking for, validity is a formal property, and soundness is a substantive property having to do with truth and falsity. So if you find the formal analog when it comes to non-deductive standards, you say it's a strong argument. That doesn't mean the premises are true. It just means if they're true, the conclusion is strongly supported. And notice that's obviously going to come in degrees. If we then add truth when it comes to the premises, we'll say it's a cogent argument as well. What about probability theory? So I said we'd talk about this one. This is about the origins of our understanding of the mathematical theory of probability, which traces to Blaise Pascal. Pascal may be more famous to you for his wager argument concerning the existence of God. But Pascal died very young. I believe he died when he was 36. He led a life of, let's just call it a life of debauchery, until he converted to Catholicism at age 31. And then he did a bunch of work in the next 5 years, including the collection of thoughts and ideas that he had that got put together as Pensée. And the wager argument is in that. We'll look at the wager argument in some detail when we get to decision theory. But the way the argument goes is you get to make a bet. You can bet that God exists or God doesn't, which involves believing that God exists or not believing that God exists. And then there are associated payoffs. If there is a God and you believe, you get an infinite reward. If there is a God and you disbelieve, that's very bad for you. If you don't believe there's a God and there's not a God, Pascal actually said you lose a few vices because believing in God is supposed to be good for your soul. In any case, he said it doesn't matter what you fill in the other two boxes of the matrix as. It's obvious the right decision theoretic strategy is to believe that there is a God. That's the wager argument. In any case, as I said, he lived a life of debauchery, and the Chevalier de Mere was one of his friends who had a gambling house. And he invented a game. So here's how the game went. So you're given a single six-sided fair die, and you have to roll it. And your goal is to avoid rolling a 6. Here's how you win, and here's how you lose. You win if you avoid a 6 4 times in a row. Otherwise, you lose. So you pay your money, you're given the die, and now you have to roll it. And if you do that 4 times in a row, not getting a 6, you win. He was making money with this game. He thought, by the way, the odds were 2/3 in favor of the house here. I'll let you ruminate on how he got that number. If you got the correct answer, if you got the explanation correct about how he got that number, that's great. But here's where it is. He knows there's 6 sides on the die. He knows the die is fair, so the chance of getting any one number, a 6, is 1/6. And you have to roll that die 4 times. That's where he got 2/3. So that's how he was thinking about the game. It turns out he was making money. He wasn't winning 2/3 of the time, but he was making money. When you're making money, you don't actually reflect a whole lot about what's going on. It's just something you go, thought I was going to make more. That would have been nice, but I'm doing fine. In any case, this game doesn't last very long. So he decided sometimes people want to play games that go on a bit longer. So let's change the game to 2 dice and replace the goal. You're not trying to avoid rolling a 6 now, but you're trying to avoid rolling a 12. And then he thought, I want this to be symmetrical with the first game. So since the chance of rolling a 12 is 1/36, and he got that by multiplying the chance of getting a 6 on each of the 2 die. What we want is a case where we can get 2/3. So the right answer is, what number times 1/36 gives me 2/3? Well, 24. So that's what he said. You play this other game, it's going to take you a bit longer, but you win if you avoid 24 times in a row and you lose otherwise. And he went broke. He writes a letter after going broke, writes a letter to Pascal and says, what went wrong? Did I have a string of bad luck, or did I make a math mistake? And Pascal figured out he made a math mistake. Notice this is symmetrically exactly the same math mistake in the New York Times article. If you remember, the New York Times article said there's a 0.15 chance intrinsically of each level of defense shooting down the plane. And so if there's 5 levels of defense, we multiply 0.15 times 5. And you could have seen very fast that that's a mistake, because if you had 10 layers of defense, nobody in their right mind would rely on that calculation to tell them the probability of shooting down an incoming plane. Notice the same thing here, just go to the simpler game. You know what the probability of rolling a 6 is. So suppose instead of 4 times in a row avoiding a 6, you made the game 1 where you have to avoid a 6 8 times in a row. Well, now it's more than certain that the house wins, because the chances of doing that are more than 1 against the person rolling the dice. So as soon as you change some of the details about the number of levels of defense, or the number of times you have to change, the number of times you have to avoid an outcome to win the game, you can see the guy's making a simple math error. Whatever we're supposed to do to calculate this correctly, it's not what he was thinking. Now, what's the correct way to think about this? There are two ways to think about this. Let's just do it with the simple game. There's your first toss. What's the chances of avoiding a 6 on the first toss? 5/6. That is a secure assessment. We know that one's right. What's the chances of avoiding it on the second toss? If you think 5/6, that's the mistake. Why is it a mistake? Because the description of the event I gave you is actually a complex event. The reason for that is you can't get to the second toss unless you avoid a 6 on the first toss. So this is really a conjunctive event. Avoid a 6 on the first toss and avoid a 6 on the second toss. If you do that, then you'll get to go to the third toss. But notice you have to keep decreasing this number as you progress through the game to take account of the fact that once you get a 6, the game's over. So take the New York Times article. First level of defense has a 0.15 probability of shooting down the plane. If it shoots down the plane, then the second level of defense, there's no probability of it shooting down the plane because there isn't a plane. So what's the probability that the second level of defense shoots down the plane? Well, it's the same intrinsic probability of how successful it is at hitting its target times the probability that the plane wasn't shot down at the first level of defense. So it's 0.15 times 0.85. Similarly, for the third level of defense, it's 0.15, the accuracy rate of these guns, which is embarrassingly low, times 0.85 squared. Same thing in the Chevalier de Mere's gambling house case. Your chance of losing on the first roll is the highest. Your chance of losing on the second roll is lower because you have to take account of the fact that you had to get through, you had to not lose, you had to avoid losing on the first roll in order to get to the second, and to get to the third, you have to avoid losing on both of the first two to get to the third. So Pascal saw quickly that that was the source of the error. He didn't see immediately how the solution was supposed to go, but another way to do it is change it to a negation problem, and this turns out to be a fairly useful strategy. You want to know what are your chances of winning the game, and to do that you have to avoid rolling a 6 4 times in a row. So what's your chances? That's going to be 1 minus the chance of losing the game. In any case, in thinking about these problems, Pascal comes to the rescue, and we've come to see that what he discovered about the mistake the Chevalier made is encoded in the following axioms. First, a probability is a number between 0 and 1. Inclusive. 0's the lowest, 1's the highest. Second, where A and B are incompatible events, the probability of A or B is just the sum of the probability of A plus the probability of B. Where A is necessary or a tautology, sometimes people call it certainty, the probability maxes out. And finally, the most important one is to understand this conditionality relationship. The probability of A given B is the same number as this ratio. The probability of A and B divided by the probability of B, provided, of course, that the probability of B is not 0, because division by 0 is undefined. So the ratio formula is conditional on a non-zero probability for the denominator, but then the ratio holds. And finally, since we have now introduced the probability of a conjunction, let's say how that one gets defined. The probability of A and B is the probability of the first times the probability of the second given the first. Those are the axioms. They help us solve lots of problems, but theorems are at the heart and soul of mathematical theory. So what we want to know is what else we can prove from these axioms. Now, there's something that we can derive from the conjunction rule itself, and it involves the notion of independence. So suppose that the truth or occurrence of A has no probabilistic effect on the occurrence of B. That is to say, B is independent of A. Well, if that's true, then the probability of B given A just is the probability of B, because there's no probabilistic effect to be found here. In that case, we can calculate the probability of a conjunction just by multiplying the two probabilities. So here's the thing that must be kept clear. There's a simple version of the disjunction rule, and there's a simple version of the conjunction rule. For conjunctions, we multiply. For disjunctions, represented by the symbol V, we add. The restrictions for applying the simple rule appeal to independence when it comes to conjunctions and exclusivity when it comes to disjunctions. And you will find yourself, when you start doing homework problems on probabilities, confusing which condition applies to which simple rule. So make sure you master attaching independence. First thing is, keep repeating this. Independence goes with conjunction, exclusivity goes with disjunctions. Independence goes with ampersands, exclusivity goes with wedges. Now, there's a special kind of mistake. I took this from a textbook that I used to use. It's a textbook, it doesn't matter which one it is, but it was by Ian Hacking. So we're thinking about independence and the conjunction rule. And here's a mistaken discussion about independence. It contains an important insight, though, because this mistake is very easy to make. Ian Hacking is an extremely good philosopher, but he made it. So the case involves the probability of both the Dodgers and Blue Jays being in the World Series, and suppose those numbers are 0.4 and 0.3 respectively. Now you want to know, so the Dodgers, the probability is 0.4, the Blue Jays, the probability is 0.3, and you want to know what's the probability of both of them being in the World Series. So that's a conjunction problem. So we want to calculate the probability of both. Multiplying the probabilities is often said to be a mistake on grounds that the two events may not be independent. That is a mistaken use of the independence restriction. All right, so you want to know, how do I figure out the probability that they're both in the World Series? So Dodgers and Blue Jays both ending up there. Can we simply multiply? The answer to that depends on whether the events are independent of each other. But notice, this remark doesn't say that. It says, no, you can't multiply. That's a mistake because the two events may not be independent. Now notice this remark talks about whether we know that the two are independent. That's not relevant to whether you get to apply the restricted rule or the general rule. The restricted and general rule is a matter of whether they are in fact independent. So of course, if you know that they're independent, it follows that they're independent. But suppose all you can say is, well, they might be and they might not. Well, the only thing that matters for whether it's appropriate to multiply here, the only thing that matters is whether if the events are in fact independent, not whether you know that they're independent. If you know that they're independent, go ahead and multiply. If you don't know that they're independent, don't rely on multiplying, but it doesn't mean it's a mistake, because all that matters is the objective fact of whether the two are independent. So be careful to distinguish when the events are independent from whether we know that they're independent. Those are not the same thing. And the worry is that you can't multiply because you don't know that they're independent. I think that's correct. We don't know that they're independent, but it doesn't matter what we know. What matters is the facts. If they're independent, then the probability that they're both in the World Series is just the product of the 0.3 and 0.4. So in that case, if we have no clue whether they're independent or not, our calculation would be unwarranted because we don't have the right information to justify doing the multiplication, but it might be exactly the right calculation anyway. Okay, so don't confuse the epistemic condition with the objective factual condition, which is the one built into the probability calculus. Now on to some theorems. What's the probability that you draw either a queen or a club from a fair deck of 52 cards? First thing to notice is this is a disjunction problem. And when you see a disjunction problem, you typically think, I get to add. You do get to add, but you can't merely add unless the events in question are exclusive of each other. Exclusivity here says they can't both occur. So you ask yourself, can I get both a queen and a club? And the answer to that is yes, you can. So these aren't exclusive events, and hence you can't use the simple disjunction rule just to calculate the probability by adding. So in a fair deck of 52 with no jokers or anything, probability of getting a queen is 1 over 13. Probability of getting a club is 1 over 4. But if you solved this problem just by adding those two numbers together, that would be wrong, because the events are not exclusive of each other. So what you can do, since you can't simply add, here's what you do. You add, but then you have to subtract the probability of both of them occurring together. This is called the general disjunction rule. We'll prove it later, and you'll see what we're doing, why we have to subtract when we do the proof. Change the problem, though, from a disjunction to a conjunction problem. Suppose you want to know what's the probability of drawing both a queen and a club. Is that just a simple multiplication problem? This is an exercise in applying the right restriction clause to the problem. Exclusivity applies to disjunctions. Exclusivity is irrelevant to conjunctions. The relevant clause is independence. So when does independence occur? Is the probability of drawing a club, given that it's a queen, the same as the probability of drawing a club? Well, you know what the probability of drawing a club is. It's 1 over 4. What's the probability that it's a club given that it's a queen? Well, now you just cut your deck down to 4 cards. How many of those cards are a club? Just 1. So the probability of it being a club is 1/4. The probability of it being a club given that it's a queen is 1/4. So the two events are independent, and hence the answer is yes, you can. The two are independent. Drawing a queen neither raises nor lowers the probability of drawing a club. Okay, so that's some information about independence and exclusivity. It's time to prove some theorems. So I already adverted to this when we were talking about the Chevalier-Demer case, that the probability of an event is the same thing as 1 minus the probability of the event's complement. Or if you prefer, the probability that a proposition is true is 1 minus the probability that its negation is true. Can we prove this? This, it turns out, is the theoretical formal work involved in understanding probability. So here's how we start. Note, to start with, that A or not A is a logical truth. So by one of the axioms, remember one of the axioms was every tautology, every necessary truth, every logical truth gets a probability of 1. So the probability of A or not A is 1. Start there. This is a disjunction problem. And note, it's an exclusive disjunction. Both A and not A can't be true. So its probability is gotten simply by adding. So if you can replace that with this addition problem, you then end up with this formula once you do the replacement. The probability of A plus the probability of not A equals 1, and then simple algebraic transformation. Subtract the probability of not A from each side, and you get that the probability of A is 1 minus the probability of not A. So that's a proof of the negation rule. It will turn out to be useful in solving many problems that we look at. I also told you in remarking on how probability respects logic on the logical equivalence claim. The logical equivalence claim is that if A and B are logically equivalent, they have the same probability. So here's some new symbols. These are derivability symbols. What it says, if I write A turnstile B, that says I can derive B from A. And if I write A opposite direction turnstile, that's the same thing as the other direction turnstile from B to A. So this is just our way of representing that A and B are logically equivalent. So assume that the logical equivalence claim is a conditional. If A and B are logically equivalent, then they have the same probability. So what we do is we assume the antecedent, and we're going to try to derive, that's the thing in the if clause, and we're going to try to derive the consequent, which is the thing in the then clause. So first, if we assume A and B are logically equivalent, this is going to be a theorem. Now, I'm going to simplify a bit here because here's the truth of the matter. If A and B are logically equivalent, then you can derive from no premises at all that if A is true, then B is true. Why? Because that's what this symbol tells us. If A is true, I can derive B. So replace the turnstile with the arrow, and then that'll be derivable from no premises at all. That's what it means, by the way, to have this symbol not be preceded by anything. So in usual cases, you put the premise before what you can derive from it. So you can derive A or B from A because A is stronger than A or B. But if there's nothing preceding the sequence symbol, that means you don't need any information to show that what follows the symbol is correct. Okay, so to simplify a bit, this will be true because first, that's true, and second, this formula and this formula are logically equivalent. This formula has a truth value which comes out true except when the antecedent is true and the consequent is false. That's the one and only case where a conditional comes out false. But notice the same thing happens over here. A disjunction, for it to be false, both of them have to be false. So that comes out false only when A is true and B is false. So those are logically equivalent formulas. And that's what underlies this first step of the proof, where I get this to be a theorem, given our assumption with which we began. Now, if A is logically equivalent to B, then this disjunction is an exclusive one. That means we can get the probability of that disjunction just by adding. Moreover, the disjunction is necessary, because if you can derive a claim from no information at all, it's a logical truth. Logical truths are all necessary. So this sum is 1. The sum of these two probabilities is 1, so the probability of B has to be 1 minus the probability of A. Now, we've already proven the negation theorem. So we have the probability start with the formula that we had here. Probability of B is 1 minus the probability of not A. And this probability just is 1 minus the probability of A by the negation theorem, which just is the probability of A. So by this sequence, probability of B is the same as the probability of A. So the logical equivalence claim is provable. Let's go back to the general disjunction rule. If the events in question are in a disjunction, are exclusive of each other, all you have to do is add. But if they're not exclusive, you have to use the general disjunction rule. To prove this, we're going to resort to a strategy that we see throughout proofs when doing probabilities, and that's to replace a claim, a simple claim, with its logical expansion across a partition. Now remember my block of cheese. The probability space in question is like a block of cheese, and you can cut up the block of cheese however you want into compartments. When you do that, you have generated a partition. Once you generate a partition, you can take any claim you want. So suppose we do a partition in terms of B and not B. This is the B part. This is the not B part. Now, A is going to be equivalent to the A and B part plus how much of it is both A and B, and how much of it is A and not B. So you're looking at how big is the A chunk in the B part and how big is the A chunk in the not B part. When you do that, you can get a logical expansion. So I'm using the symbol plus here, but notice that A is the same as A and B or A and not B, because either B is true or not B is true. So since A is logically equivalent to this disjunction, we can replace A with this. That's what I'm doing here at this step, at these two steps. I am replacing the probability of A with its logical expansion in terms of probabilities, and I'm replacing the probability of B with its logical expansion. So what I'm doing is I'm expanding A across the B not B partition. I carved the block of cheese into the B part and the not B part. And then here I'm replacing B with its expansion across the A, not A partition of the space. This is going to turn out to be an extremely productive thing to do in many probability proofs. And it keeps being used in even really high-level postgraduate work that you might do in probability theory. So in any case, A is equivalent to A and B or A and not B. Those two events are exclusive of each other, so we'll replace the or with a plus sign. So the probability of A is the probability of A and B plus the probability of A and not B. And expanding B across the A, not A expansion, and then switching positions. I could have written B and A and B and not A, and then commuted to A and B, and then to not A and B. But it doesn't matter how you do that. It's very easy to see that commutativity is a property of conjunctions. It's also a property of disjunctions. But in any case, that's how we're going to start this proof. Expand A and B across relevant partitions. That's the first thing. So then add up the whole thing. The probability of A plus the probability of B is just the sum of these four probabilities put together by summing. Now, subtract the probability of A and B from both sides. We still have an equivalence, so that's fine. And note then that A or B is logically equivalent to A and not B, or A and B, or not A and B. Well, an or statement is false in only one case, when they're both false, because or is a very permissive connective. It tells us either the first is true or the second is true. So second one's true here, first one's true on the second line, they're both true here. So it's false in only one case. So A or B is logically equivalent to the first three lines. The fourth line, it's not logically equivalent to anything involving the fourth line, because that's where it comes out false. So this formula will be logically equivalent to A and B are both true, A is true, B is false, or A is false and B is true. And that's just what we have here. First true, second false, both true, first false, second true. Now that's relevant because we've already proven something about logical equivalence. We know what to say about the probability of two claims when they're logically equivalent to each other. That's what the logical equivalence theorem did for us. Notice as well that these disjunctions here are exclusive. This, if that one's true, that one's false, and that one's false, and the same for the others. So they're all three exclusive of each other, so we can just add. But if we do that, notice that's just the right side of the previous equation. And thus, the right side of the previous equation gives us the probability of A or B, because it's logically equivalent to that, as we've already shown. So that's the general disjunction rule, and that explains why the probability of that just is the probability of A or B, and that's given by adding the two probabilities together and subtracting their joint occurrence. Now notice, if A and B are exclusive of each other, this number, probability of A and B, will be 0. That's why when you have exclusive events, you can use the simple disjunction rule rather than the general one. So as said already, the probability of A plus the probability of B minus the probability of their conjunction just is the probability of A or B. We need also to talk a little bit about conditional probability, because that'll be essential in applying probability theory to confirmation cases. First, remember the ratio formula. The conditional probability of A on B is the ratio of the probability of A and B divided by the probability of B, provided that the denominator is not 0. So what's the probability of rolling a 6 given that you've rolled an even number? Well, it cuts the space in half in this case, because half of the numbers 1 to 6 are even and half are odd. So the even ones are 2, 4, and 6. So the probability is 1/3. What's the probability of drawing 2 aces in a row? You should, I hope you look at that and say, I can't answer it. And you'd be right if you say that, because when you do, you got 52 cards in the deck, so pick a card. What's the chances of it being an ace? 4 over 52, which is 1 over 13. What's the chances of the second card drawn being an ace? The answer is you don't know until I tell you whether I replaced the first card before drawing the second one or not. So this problem is under-described. If you do replacement, then it's 1 over 13 times 1 over 13. If you don't replace, then the two selections are not independent of each other. So that would be 1 over 13 times 3 over 51, because that's the probability of drawing an ace on the second draw, given that you drew an ace on the first one. So that's an under-described problem. With or without replacement is crucial. Last example, I think it's the last one on this page, maybe it's not. Next example on this page, the gambling house case. Well, I already went through this. What's the chances of avoiding a 6 on the second toss? Well, that's the probability of avoiding a 6 on the first toss times the probability of avoiding it on the second. So 5/6 times 5/6 for the second. And so on. You can calculate the entire problem that way. I think the answer is in game number 1, the probability of the house winning was about 52%. In the second game, when you went to 2 dice and you were trying to avoid a 12, I believe the probability is about 48, but you can calculate that. I haven't done it for a while, so maybe I'm misremembering. The total probability theorem I went over before. That has to do with partitions. Bayes' theorem is the last crucial theorem that we're going to talk about. So the simple version says probability of H on E is a function of the probability of E on H, which is the degree to which the hypothesis predicts the evidence. So if you recall, a guiding insight that we've been talking about is that confirmation is the mirror image of prediction. When you have a theory or a model or a hypothesis, you're looking at what it predicts about the course of experience, and the degree to which it predicts something helps determine the degree to which seeing what was predicted confirms the proposition. There's also something else involved, which is the degree to which the data is surprising. And if we call this the Bayes factor, we can think of that as the other factor. Remember, in the Geary program, we have to ask the question, if we get agreement between data and prediction, was the agreement likely? That gets measured by the Bayes factor. So first we want to know, does the theory predict the evidence? And then, was the agreement likely? How surprising is the data? Think of the Bayes factor as characterizing the degree to which the data is surprising, and this inverted conditional probability as the degree to which the evidence is predicted by the hypothesis. We can also expand, once you see the total probability theorem, we can expand this denominator Remember how logical expansions work. You look for our partitioning on our block of cheese, and then you replace E with however you did the partitioning for each partition. Now, if you do the partitioning in terms of H itself, H and not H, then E is equivalent to E and H, or E and not H. And then this probability, by the conjunction rule, is this one. So we can replace, notice what we're doing is we do a logical expansion on the denominator here in terms of E and H, or E and not H, or if you prefer, H and E, or not H and E. And then what's the probability of H and E? It is the probability of H times the probability of E given H. What's the probability of not H and E? It's the probability of not H times the probability of E given not H. That's the expanded form. It turns out that's useful because if you partition in terms of your hypothesis and its negation, you get to eliminate at least this unconditional probability. Notice you've already got to have an unconditional probability for H, but we had a conditional probability here and a conditional probability here and two unconditional probabilities. If we can reduce the number of needed unconditional probabilities from 2 to 1, that would be great. And notice that's what we do. We've got to have the probability of H, but then in the denominator, we end up with the probability of H and the probability of not H. If we've got the probability of H, by the negation rule, we can calculate just by subtracting from 1 to get the probability of not H. So we don't need, once we do a logical expansion that way, we don't need two unconditional probabilities, but rather only one. All right, that's Bayes' theorem. Now, Bayes' theorem has the most, maybe the simplest proof in the history of mathematics for something that turned out to be so enormously significant. There's another one, Nash's equilibria points in economic theory, decision theory. It's actually in game theory. It turns out to be an enormously useful notion, the notion of an equilibrium point in game theory, but the proof of it is unbelievably simple. Here, the proof of Bayes' theorem is unbelievably simple. So it's not the complexity of the proof that amazes people. Bayes gets his name on this thing just because the theorem turns out to be so useful in so many different areas. So how does the proof go? Well, first, start with the ratio formula. That's the ratio formula, which helps us understand what conditional probability involves. Notice then that H and E is logically equivalent to E and H, and the probability of E and H is, well, actually, this is the probability of, I didn't need this step. Forget that part. The probability of H and E is this. Probability of the first, and then I commuted after doing this, times the probability of the second given the first. Then commute and you get what I wrote down there. So what we're going to do is replace this with this. If we do that, we end up with the simple version of Bayes' theorem. Probability of H given E is the probability of E given H times the probability of H divided by the probability of E. So the proof is unbelievably simple. The significance of it comes to when we apply it to bodies of evidence. So we want to know what the probability is of a hypothesis on a given body of evidence. Bayes' theorem tells us we can calculate that if we know how surprising the data is and how much the hypothesis predicts the evidence. So consider this very simple medical test example. Suppose you know this. This is called the base rate. So when I talked about the base rate fallacy in the last set of notes, I said we'd skip it and talk about it here. So the base rate fallacy is ignoring this piece of information. So suppose 1 in 1,000 have a rare disease, and there's a test for it, and your doctor's advising you to take the test. So the test, here's what we know. The test gives a false positive 5% of the time. A false positive is this. The test says you have the disease, but you don't. And let's suppose the test never fails to detect the disease if it's present. So that's the false negative rate. You take the test and you test positive. How likely is it that you have the disease? You're going to freak out. Doctor asked you to take a test because he's worried you have this disease. You take the test and the test says you have the disease, and damn, it's a pretty good test, right? It's not like flipping a coin. It's not like reading entrails from a goat that your favorite psychic asked you to do. It's not the tarot card reader who went and consulted that. This is a good, well-documented test. False positive rate of 5%, a 0 false negative one. How likely is it that you have the disease? Well, the fact is, that's what we use Bayes' theorem for. Cases just like this. It turns out everything we need to know to apply Bayes' theorem is contained in this description. Of the numbers. So let's try to do it. So remember, the first thing is, what's the probability of the hypothesis? The hypothesis in question is that you have the disease. So what's the probability of the hypothesis? Well, that's the probability that you have the disease. And the unconditional probability of that is given by the base rate, which is 1 over 1,000. We also know that the probability of a positive test, given that you have the disease, is 1, because the false negative rate was 0. So the probability of the evidence, the positive test that you got, given that you have the disease, equals 1. And so that will, of course, when we did Bayes' theorem, we did it in terms of H and E. So that would be the same thing as the probability of E given H, if we want to apply the variables we used when we did Bayes' theorem initially. Okay, so the probability of the hypothesis independent of the evidence was 0.001, because 1 in 1,000 have it. If we multiply these numbers and divide by the probability of the evidence, we have our answer. So what we were looking for is the probability of you having the disease given the evidence, and by Bayes' theorem, that's the probability of the evidence given the hypothesis times the Bayes factor, which is the probability of the hypothesis divided by the probability of the evidence. So we know this number. We know this number. We got to do something with the probability of the evidence. And that's where we do the logical expansion in terms of a partition to make some progress. So what's the probability of the evidence? Well, the probability of the evidence, if we expand it across the H, not H partition, is this. Probability of H times the probability of E given H plus the probability of not H times the probability of E given not H. Now, as we said already, we already know that number. If we know that number, we can get that number. We have this number already. That's going to be 1. The only one we're missing now is this one. What's the probability of the test coming back positive given that you don't have the disease? Well, remember, we had both a false positive and a false negative piece of information reported. The false positive is 5%. So that's the number. This number is 0.05. So now notice we have everything we need. Every number in this denominator can be given, can be calculated, and once we have that, we can apply Bayes' theorem. So we know probability of E given, probability of a positive test given that you don't have the disease is 0.05. The probability that you don't have the disease is 1 minus the probability that you do, which was given. So up here for not H, we get 0.999, and we already knew that the probability of a positive test if you have the disease is 1. So we have all of the numbers needed to calculate. So the probability of E, the denominator, on the right side of Bayes' equation is, you can get out your calculator and verify this, but I'm pretty sure this is right, 0.05095. Now we plug that number back into Bayes' theorem with the other number, and we get that the probability that you have the disease given the positive test is a little under 0.02. So let's just say let's round it up. The probability is 0.02 that you have the disease. Now remember, when you first heard the results, you were imaginatively putting yourself in a situation where the doctor says, I need you to take a test. I'm a little bit worried about you. And you say, okay, and you're already a bit anxious because this is not a fun disease. So you're already a bit anxious. You take the test. The doctor calls you the next day and tells you, we did the test. Sad to say it came back positive, and now you're just freaking out. All right, but now look at the numbers. The probability that you have the disease is about 0.02. It's not even remotely likely that you have the disease yet. What's important here is not the flat probability, but the fact that your probability went from 0.001 of having the disease to, based on all the information we now have, to 0.02. So that's an increase of 20 times. It's now 20 times more likely that you have the disease than it was before you got this new information. That's a pretty significant and powerful test if it can raise the probability that much. But this is, by the way, one of the reasons why you're recommended to get a second opinion in medical cases like this, or to do other diagnostic tests to try to confirm or disconfirm the initial results. The number didn't go up enough for the information to be actionable on the basis of that one test. So suppose you run a number of independent tests. You can actually calculate how many independent tests of the same power that this one had would you have to take in order for it to become more likely than not that you have the disease. I think the answer is 4 or 5, but I'll leave that to you to see if I'm correct in that number. All right, now if I were going to give you a test on probability theory, a test that included the information on probability theory, you might want to see some sample test questions. So I'm not going to go over these or the answers. I'm just pointing to this being part of the slides for this part of the course. And we will, instead of using class time to talk about these, we'll use office hours in place of class time, because some of you will be able to solve these fairly intuitively and quickly. And some of you will need help, or maybe some of you need help with some and some help with others. So if I just prattle on, is that a good way to put it? Prattle, P-R-A-T-T-L-E. Try not to be a prattler. Anyway, if I just prattle on about how to solve these problems, it will generate a whole bunch of video time that will not be needed by many of you. So let's talk about these things, about these sample test questions during office hours. So notice Some of the test questions are going to specify with replacement for a fair deck, and some without replacement. And then you have to figure out what the probability is of various ones. There are probability problems have to do with little balls in a bag or little marbles in an urn, things like that. So there's some, and coins and boxes containing coins. So take a look at all of those. More sample test questions. I just want you to have an idea of what sorts of things I expect you to have mastered in order to be able to take a test and move on into the statistical and causal studies that we're going to spend more time talking about. Finally, at the end of these slides, if I were going to give you an in-class test, I provide these last pages, this last page, so that you don't have to memorize each of the axioms and the theorems that we proved in this lecture. They are important, so I included them at the end of the slide. For a primarily online course, it's not really necessary to give you these because you have access to these anyway. It would only be for in-class exams. So you'll have to remember these. It's important that this is really the important stuff that we went through about probabilities, and then the rest of it is just figuring out how to apply this information to solve particular probability problems.